We're here in section 5.1, and we had just gone through different ways of setting heights for rectangles when we're trying to approximate the area underneath a curve. So we saw left endpoints, right endpoints, and midpoints. We saw what it looks like to have an overestimate, an underestimate, and then with the midpoint rule, it was really hard to tell if we were overestimating or underestimating. So we had gotten down to this estimate of the area that was closest from what we could tell with 4 rectangles in the midpoint rule. We were estimating the area under f of x equals 1 minus x squared. All right, from x equals 0 to x equals 1. We were estimating so far that that area was approximately 0.671875 square units. That's the best we could get for right now. But if you want to know the actual area underneath that curve, that's basically what we're going to be doing it over the course of the next couple sections. So for this section, we really are just focusing on getting the most accurate estimates we can right now. And if you want to get a more accurate estimate, one of the main things you can do is to use more rectangles. Okay, the more rectangles you use, the more accurate your estimate is going to get. At the very start of looking at this function and that area, we first started with looking at just 2 rectangles and finding their areas and adding it together. We got 0.875 units for that estimate. We knew that was an overestimate. Now, we went to 4 rectangles and we brought our estimate down to 0.87125, which is still an overestimate, but we were getting closer to the actual area. If we were to double the number of rectangles again, we would get even closer. But there comes a point where doing it by hand becomes not so realistic anymore. If you are adding together the areas of, 20, 50, 100 different little rectangles, you don't particularly want to calculate that all out by hand. So you can use your calculator most definitely. And there's also some online tools that can help with this. So the one I've pulled up for right now is opengraphingcalculator.com. All right, old favorite of mine from my old computer science professor. Desmos.com also has a nice calculator for this. It shows you all the little rectangles. There's a variety of settings you can play around with. So if you guys want to try that one out, the link is on the notes. Okay, but just to demonstrate for you, on Open Graphing Calculator, let's put in our function here. So f of x equals 1 minus x squared. Let's see. I've got to find the squared button. There we go. 1 minus x squared. All right, so there's our parabola. All right, let's zoom in on that little guy. Okay, and we are just trying to look at the area underneath this curve from x equals 0 to x equals 1. So we can get really close in there, looking at the portion of the curve that we want. Okay, now on here, let's see, what's this called? Toggle button there. Has some extra little tools for calculus if you click this button. Okay. If we set the number of rectangles here is given by n, and there's a little slider here. So let's just do n equals 4 for right now so we can see if we match our old answers. A and B are the ends of the interval that you want to look at for the area. So we want to go from 0 to 1. So A is going to be 0, B is going to be 1. We'll keep n equals 4 for right now. And then this little button here where it says right at the moment, that's the different types of endpoints that you can use. So right endpoints, left endpoints, middle points, that's our midpoint rule. There's also some extras here, trapezoidal, lower and upper sums. Trapezoidal we don't really encounter in this class. Lower and upper sums are some terminology that the book uses, so you might want to play around with those as well. So let's put it on left endpoints for right now and press this little guy right here. And you'll see the rectangles show up. All right, right in that area that we were looking at. So this is like the top sketch on our page with the 3 sketches, 4 rectangles and left endpoints. So you can see it matches our picture. And then the approximation for the area is given right here. Okay, or there's that funky little E looking shape. That's a thing called a sigma, and we're going to look at that in section 5.2. But the approximate area is 0.7813. And notice on our notes, we had gotten 0.78125. So that would round up to 0.7813 if you're only doing 4 decimal places. Okay, so let's also check our right endpoints. Yeah. So this is like the middle sketch on our page with the 3 sketches. This was where we had 4 rectangles, but the last rectangle was that funky little flat thing because the right endpoint of that last rectangle is at x equals 1, where the height is nothing. So you can see that, yes, it really is a flat little nothingness rectangle down there. And so we add together these areas set by our right endpoints, and we get approximately 0.5313. On our notes, we had 0.53125, so it fits. Okay, and then on our last sketch, we had done the midpoints. So here's midpoints. There we go. You can see a really nice sketch, nicer than my hand-drawn sketch, I'm sure. And then you get an estimate of about 0.6719. We had 0.671875, so rounding. This only rounds to 4 decimal places, so to 4 decimal places, it's a match. So the beautiful thing about doing it on the online calculator is that you can change your number of rectangles really easily. So real quick, I'm going to go back to, let's do left endpoints, and I'm going to bring us up to, let's do 10 rectangles. Okay. Yeah, there we go. Yeah. A little bit sensitive there. Okay, so with 10 rectangles, you can see the sketch done really nicely, probably better than we would do by hand, just saying. And then we get an area approximation of about 0.715. You might say, hey, that's a little further off. It's because I went back to left endpoints. If I did 10 rectangles and midpoints, we could see an estimate of about 0.6675 for the area. That's looking pretty good, right? Those rectangles are fitting pretty closely to the shape of our parabola. Let's try doubling the number of rectangles here. Take it up to, say, 20 rectangles. And now you can see that it's getting even closer to matching the shape of the parabola. Okay, the differences, especially in this first part of the curve, the differences between the rectangles and the parabola itself are getting smaller and smaller. We've still got some gaps down in here, some little overflows and some little undercuts, but we're working with midpoints, so this is still a pretty good estimate here, an area of about 0.6669. okay? And let's just max this thing out here. Let's take it all the way to the top, which I think is 100. Okay, so there's 100 little rectangles underneath there now, and we're using midpoints on every single one of them. You would not want to do this by hand. Um, but look how close that fits to our parabola. The yellow shaded area of the rectangles is basically what we're looking for. That's the area under the parabola from what we can see. If you zoom in a lot, you can see that there are still some little overhangs and undercuts, but they balance each other out pretty well because of the midpoints. Okay. Even if you switch this to right endpoints, even if you switched it to left endpoints, it still fits pretty closely. Midpoints, I think, is the prettiest. Um, and we get an area of about 0.6667. Now, what this actually is, because this is rounding to four decimal places there, this is just 0.6 repeating, 0.666666666, on and on and on. And if you think about what that actually is in terms of fractions, the actual area underneath this parabola, 1 minus x squared, from x equals 0 to 1, the actual area is 2/3 of a square unit. And so this approximation with 100 rectangles saying 0.6667 is really, really close. That is pretty darn on it. And if we could increase this number of rectangles even more, that estimate would just get even better. It would keep matching up to more and more decimal places, more and more sixes there. But yeah, the actual area is 2/3, and this looks like a really good estimate. So if you want to play around with this, there it is.